Good evening, everyone. Thank you so much for staying so long. I'll be giving the concluding talk of the conference, following up on a very interesting talk from Yang Chen. I was actually worried that maybe after the talk, everybody would be leaving, but thank you for staying on. I am very kind of honored to be here. I want to talk about some of our research. I will not have time to touch on everything that I would like to. Instead, I'll keep my talk very focused and talk about some of our initial results on this kind of idea of trying to step back from kind of all the problems that we were working on, heat transfer and Casimir physics, but step back and look at actually properties of matter in a lot more detail. And this really goes to the theme of many of the talks that we have heard today throughout the day, including that of non-locality, graphene, some of the very interesting boundary conditions that Gang mentioned in his talk. So it does connect all of these ideas together. So I think it's a very good fit. But before I start, I do want to mention a very big thank you to the organizers. I was not able to be here for the longest time that I wanted to be. That's because I had some personal work in India to attend to. But even though I've been here for a few days, it has been really nice talking to a lot of old friends and also making some new friends. So thank you very much to the organizers for bringing the community together. So everything I'll be presenting today, I want to mention that all the credit goes to my team. We've been growing in a couple of different areas, so I won't talk about all of that, but I did want to mention that for collaborations, we like to choose problems somewhere at the interface of, say, fluctuational electrodynamics, quantum optics, and also materials physics. And I'm a theorist by training, but over the years, we have formed a lot of experimental collaborations, and many of my students are very closely involved in experiments as well. So I'll be happy to talk to you more about this. You've probably met and talked to one of my postdoctoral scholars, a very bright postdoctoral scholar, Dr. Adrian Rubio Lopez. Many of you kind of already know him, so I probably don't have to talk about his research or his poster, but he's here for at least a day more, so I hope you kind of talk to him in detail. So today's talk is going to be focused, and I want to talk about work done by my postdoctoral scholar, Todd Van Mechelen. The other is Dr. Satwik Bharadwaj and my PhD student, Wenbo Sun. Acknowledgements to the funding agencies for supporting us for a long time. And I will be talking only about theory, and I will be very happy if I am able to convey just two key ideas in this talk. So what are those two key ideas? One, I want to talk about the concept of a Maxwell Hamiltonian. And the other idea I want to talk about is that of the susceptibility tensor, but with a small twist, and that is an atomistic susceptibility tensor. So these are the two things that we want to talk about theoretically and put them together. So for any theory, really the worth of the theory is the experimentally testable predictions that it makes. So with that motivation, I want to first tell you about the theory and then apply it to two model systems and show you that this does lead to some interesting insight which would not have been possible without this theoretical machinery. So the first one I want to talk about is graphene, but with electron-electron interactions such that graphene's electron cloud is modeled as a hydrodynamic fluid, and then you apply a magnetic field. So for this specific system, the Maxwell Hamiltonian and the atomistic susceptibility tensor actually shows the existence of a topological invariant. Think of it as a quantum number. That is very unique, and it is unique to the electrodynamics of this hydrodynamic fluid. So I'll talk about this, and I'll talk about this optical invariant in detail. And after that, I'll just have a couple of slides. This is work in progress, and I'm happy to discuss kind of more details and also get insight from the experts over here. I want to apply the same machinery, but to another material, something we all know and we actually study in kind of solid state physics, in kind of introductory solid state physics, and that is silicon. So we want to look at this lattice of silicon and try to apply this machinery, and we think there are some interesting insights that actually come about, and we are noticing the existence of some waves which are only present when you start looking at this atomistic response function. So that's really the plan for today's talk. Now, where is the motivation for all of this? The motivation is really looking at the differences between macroscopic electromagnetic fields and the atomistic fields inside matter. So when you look at an experimental measurement, most often than not, you're really dealing with kind of averaged macroscopic quantities. But we know that these electric and magnetic fields that are passing through matter are actually scattering from the atoms. So there's definitely an atomistic field and there's a macroscopic field. So this problem has been addressed for a very long time. And one of the first people who actually looked at it very carefully is Clausius Massotti and also Lorentz. This was actually late 1800s. And they had a classical model. We still use it because it is really powerful. And what they did was actually connect the concept of a macroscopic dielectric constant to microscopic polarizability. And the way they kind of moved on this problem is by assuming that some of the kind of materials of interest are made of cubic lattices. I mean, this is just an assumption. They even applied it to water. And they showed that we have these small dipoles that are actually arranged on this cubic lattice. And then you can find a connection between the macroscopic dielectric constant and the kind of molecular polarizabilities. And this is completely classical. And later on, Lorentz also had kind of frequency dependence and refractive index inside the theory. Please remember that this is before quantum mechanics. Now, once we had the quantum theory, it did take some time, but there's a very influential and fundamental paper that revisits problems like this, but in a completely quantum context. And this is in 1962, a very famous paper, and this is known as the Adler-Weiser theory. What Adler and Weiser did was they looked at these kind of wave functions on a lattice, and they looked at the density matrix of the kind of electrons in a periodic solid. And then they were able to connect the macroscopic dielectric constants to correlation functions inside matter. And more specifically, they looked at the charge and current correlation functions, and they were able to actually put some of these kind of ideas on a much more rigorous quantum footing. But one thing I want to mention is that when you actually average off these microscopic fields, this leads to loss of crucial information. And this is true in both the theories. And what do I mean by loss of crucial information? So that is really the subject of today's talk. And as many of the members in the audience noted today, and much of the research community really believes, this is an exciting time to be working in this field of thermal and quantum electrodynamic fluctuations inside matter. We really think that going ahead, we're going to see lots of interesting phenomena that are actually beyond this macroscopic averaging of fields. And this is what I want to present today. This is some of the papers. And like I mentioned, this is the two ingredients that go into it. So what are the type of questions that you can answer? So one of the things is actually what I'll talk about today is the idea of a quantum number, but a topological quantum number that is beyond the ideas of Chern numbers and Z2 invariance. I'll touch on this. And we also think that understanding fluctuations, there can also be cases where the atomic lattice symmetries really matter in the understanding of the fluctuations. And there could be other problems that are interesting, kind of order parameters inside matter related to spin angular momentum photons, possibly new anomalous atomistic waves. So these are the type of things that my group is interested in, and I'll touch upon just two of these ideas today. So where do we start? We go back to the 80s, And there are lots of really nice papers. I pointed out a few of them from Michael Berry, Marlon Scully, and Haldane. What they looked at was in vacuum, they looked at just Dirac and Maxwell Hamiltonians. And what they, some of these papers show very nicely is that if you write down the Dirac Hamiltonian, and this is for the 3D space, and there is actually no mass here. So if you write down just the Dirac Hamiltonian, have some wave function, as long as you work in this nice basis, this is known as the Riemann-Silberstein basis, your Maxwell's equations can also be written in this Hamiltonian form, and there's a nice analogy between these two. And what you can show is that the Dirac Hamiltonian has this momentum vector kx, ky, kz, and the Pauli matrices sigma x, sigma y, sigma z, whereas the Maxwell Hamiltonian also has the momentum of the photon kx, ky, kz, and the spin 1 matrices. And this is actually one way of looking at the two different symmetries of the fermionic fields and the bosonic fields. That this is a spin half system, and this is a spin 1 system. Now, one thing which is not so obvious, but it can be shown, is that the time reversal symmetry operator for the Dirac Hamiltonian, this will square to -1, and that is also kind of directly connected to the fact that we are looking at fermionic symmetries. And if you write down for the Maxwell Hamiltonian, what is the time reversal operator? The time reversal symmetry operator squares to +1. So this is an integer spin system, and all of this is consistent. So in the 80s, one of the early success of the theory was showing a very nice and intuitive result. The result was as follows. If you look at the three-dimensional vacuum and you look at massless, the massless case, you can show that in the Dirac Hamiltonian, you will have linearly dispersing states, no mass, and this is the 3D case. Same thing, of course, we know for the Maxwell's equation and Maxwell Hamiltonian, we know that you have linearly dispersing states and no mass. But the interesting kind of point that is was made was that in the momentum space, if you look at this kind of zero frequency point over here, in both the theories, you actually have a monopole sitting there. And this is a special monopole because it's a magnetic monopole in momentum space. Now, if you study it further, what you can show is that this magnetic monopole, which exists in both the theories, is completely symmetric. In the Dirac case, it is actually half integer charged. It corresponds to the half integer spin, which is that the fermionic degree of freedom. And in the Maxwell Hamiltonian case, it's actually an integer spin, and this is representative of your integer spin system, and it's an integer charge to the monopole, and this corresponds actually to the bosonic degree of freedom. So these were some of the successes. The interest kind of waned over the years, and one thing I wanted to mention is that even though the vacuum has been studied in a lot of detail in the 80s, it was actually never applied to materials physics. And these have been this has been the motivation for us to look at the problem, and these are the various papers that we have written as the theoretical tools that we are developing to be applying this to materials physics. And I'll give you a flavor of some of these papers. So what is the first result that we found when we try to apply the theory to materials physics? The first one is an intuitive idea of an effective photon mass in a two-dimensional system. So let's consider a two-dimensional material and start looking at the same analogy, but now not in vacuum, but inside a material. So in the Dirac Hamiltonian case, once you start looking at this two-dimensional system, you can actually again write down the same Hamiltonian, but now you add in, say, a massive fermion, and this is some effective mass for the electron, and that enters through your sigma z Pauli matrix. Now you can ask the question, what about the photonic case? In a two-dimensional material, what about an effective photon mass? So from just symmetry arguments, you can say, well, let's try to understand what would happen if you had this extra term. Now, let me plot the images that will help you kind of understand this better. The massless case is right here. right? And now you add in some effective mass. In this two-dimensional case, the effective mass has some very specific symmetries, and also it opens up a band gap to low energy electron waves in the Dirac equation. So this is just a picturestic depiction, and you have a low energy band gap to waves, and you have some dispersion over here, some energy momentum relationship that occurs in the Dirac Hamiltonian, extremely well known. Now in the Maxwell Hamiltonian, you can think that there could exist an effective mass term which has the exact same symmetries. In particular, it has to break time reversal symmetry, because in this two-dimensional case, that's exactly what happens in the Dirac Hamiltonian. And then you open up also a band gap to low energy electromagnetic waves. So this is a sort of effective photon mass. Then the question becomes, what is the physical mechanism that gives rise to such a term in a Maxwell Hamiltonian? So this is kind of the subject of these two papers. And the answer is that you will, if you have a two-dimensional material in an external magnetic field, the Hall conductivity, which is a property of the electrons, that enters as an effective mass in the Maxwell Hamiltonian. So in other words, the response of matter, and more particularly the T-symmetry broken off-diagonal components of the say dielectric constant of the susceptibility tensor, that enters actually as an effective photon mass and creates a low energy band gap. Now this sort of a band gap is what is known as a trivial band gap. So there's nothing interesting going on, it's just that low frequency waves are just not allowed inside this two-dimensional material because of the fact that you've applied a magnetic field and there's some Hall conductivity. So thinking ahead, we kind of realize that you can actually have a dispersion to this effective photon mass. And what do we mean by dispersion? Means we are talking about a momentum dependence to that effective photon mass. So this is a term, think of this as a m of k, this is the effective photon mass, and this is a quadratic dispersion in a rotationally invariant two-dimensional material. Now, it took us a little bit of time, but then this actually has a very nice interpretation. So let me just give you the interpretation. In a two-dimensional material, two-dimensional electron fluid, once you apply the magnetic field, you can not only have a Hall conductivity, but for a 2D quantum fluid in a magnetic field, you can also have a very unique stress-strain response. So what do we mean by that? So this term right here actually connects to what is known as Hall viscosity. Now if you take a conventional fluid, and let's say inside there you try to perform some small rotation, then you have shear viscosity that is actually a dissipative form of viscosity, and that is essentially slowing it down. So one simple way to think about it is honey is more viscous than water. There's more dissipation going on in honey as it tries to flow more than that of water. So that's the simple intuitive form of kind of viscous dissipation that we know about. But once you apply a magnetic field and inside a two-dimensional quantum fluid, you can also have a non-dissipative form of viscosity. And the way you understand that is that you have, again, this same rotational motion, but orthogonal to that motion, you actually have some energy stored inside the fluid, and this is a non-dissipative form of viscosity. And there's also been some early work on this, just this concept of Hall viscosity. So the key idea that kind of came to us was that this is a effective dispersive photon mass, and it's very nice to be thinking about this theory in more detail. Now there are some technical things in here. I'll like to ask the chair how much time I have, and 10 minutes? Yeah. So I will leave the technical stuff for later and instead just start talking about the application, because this is, we've heard a lot about the fluctuation dissipation theorem in this talk. So now that I spoke a little bit about this concept of Hall viscosity, concept of effective mass, now where can we apply the theory and try to get some more insights? So the question we started asking is, what is the connection between the fluctuation dissipation theorem and aspects of topology, which is where these concepts of effective photon mass really came in the first place. So if you have just fluctuations inside a material, now we all know that it's connected to the dissipation, and which is a form of viscosity, and it exists over all frequencies and momenta. So it's a ground state noise that populates all frequencies and momenta. So that led us to think that let's try to apply the theory to the idea of topological electrodynamics, and more specifically to atomistic crystals, and start looking at bridging the gap between a very big field of research, which is photonic crystals and metamaterials, and the idea of atomic crystals. So let's apply the theory to the hydrodynamic fluid, and in this case we are going to look at a graphene lattice. Now in the case when you have very low impurities and you go to the correct temperatures, it has been shown that the electron-electron interactions can dominate electron-phonon interactions as well as electron-impurity interactions, and you can express the graphene electron fluid as a hydrodynamic electron flow. So this is for a very specific condition. Then you can apply a magnetic field, break the time reversal symmetry, and then study what is happening to this two-dimensional electron fluid. So what we did was look at this model. It is a form of a modified Navier-Stokes model. And then you can derive the transverse response of this hydrodynamic fluid. So this transverse response has a frequency dependence, momentum response, momentum dependence, and you can think as the response of a charged viscous fluid to photons. And for the same fluid, you can define a longitudinal response and derive that, and this is what you get as chi L. And what we call as the atomistic susceptibility tensor is this chi response, which has both longitudinal and transverse, frequency dependence and momentum dependence. So the key idea here is that we can define a topology of this atomistic susceptibility tensor. So instead of looking at a kind of conventional Brillouin zone, which is wrapped onto a donut, for the hydrodynamic fluid, we actually do not have this sort of a geometry at all. The geometry that exists for the hydrodynamic fluid is actually a sphere, S2 cross S1 surface, and again, these are some technical details that I don't have so much time to go over, and sorry about that. But we can show that there is a closed surface over which you can define a topological quantum number that talks about the winding of the susceptibility tensor itself. And if you look at the susceptibility tensor in detail, you can actually have attractive Hall viscosity. So the viscosity is the same direction as the Hall conductivity. It sets up some internal fields in the same sign as the Hall conductivity. In that case, you actually have just the same trivial band gap. But in the case where n is 2, you have the interesting case where the band gap supports new types of waves which are only unidirectional, and it closes the gap. So just for 2 minutes more, I'm going to skip the experimental part, and in the last 2 minutes, I'll just talk about applying the same theory to silicon. So what you can now do, so that was just the graphene problem with repulsive Hall viscosity, gives a very interesting band gap closing and a topological quantum number. We can start looking at silicon. So we started with the atomic lattice of silicon, get the electron band structure by some of the older techniques. And then from there, we can actually go a little bit beyond the Adler-Weiser theory and start looking at the atomistic susceptibility over the entire frequency and momentum range. So this is what it looks like. It has frequency dependence, it has momentum dependence, it is transverse, and it also has the lattice symmetries. In that case, you can actually get a new eigenvalue problem with the Maxwell Hamiltonian. So this is what this new eigenvalue problem looks like. It's a Maxwell Hamiltonian which includes the local field effects with the correct symmetries as this silicon lattice. That's what we're trying to show in this picture. And I'll just kind of conclude maybe in a minute with just this figure that let's look at the conventional picture of just waves in a solid. That's the left-hand side. This is what you would get with a simple macroscopic local theory. Right here is kind of your light line. Oops, sorry. Light here is your light line, right? And then this is the gap to waves. This is the silicon permittivity really becomes metallic in this range, and again you recover the light line. So this is the macroscopic local. You can also have a macroscopic non-local model, and in that case you have some qualitative deviations from the macroscopic local model. So this does not include any local field effects, does not include the lattice symmetries at all. But now if you include the local field effects and the lattice symmetries and solve the Maxwell Hamiltonian eigenvalue problem, you definitely recover the regular bands shown in blue. But what is interesting is that there is a qualitative new physics here, because you actually see there's a new branch, and this branch has very rapid variations over the lattice. And this is the kind of interesting band that we think should be experimentally measurable. So we've just this paper which is kind of under review, and I thought this would be nice to mention. And we think that there should be ways to actually measure this experimentally. I should mention also that this particular branch is tough to measure because absorption in this range presents a challenge. But we've been looking at other materials and also other frequency ranges to find these branches in ranges where absorption does not dominate. So with that, I'd like to conclude my talk. I do want to mention that we're trying to really collaborate with many different theories, and we have some online seminar series that we have started. We hope to kind of rope you in, many of you, to kind of for collaborations. You can read more about it over here. But the idea that I want to leave you with is that we've been successful in trying to understand graphene with a very specific quantity, like repulsive Hall viscosity. And we've been able to show that when you have that, there are special edge waves and a band gap closure. We've also applied the theory to silicon, and we're working on it, and we think there are some anomalous atomistic waves which are not present in a conventional homogeneous theory. Now, we are cautiously optimistic that these two theory predictions are correct, and we are working with experimentalists on this. And if indeed these are correct, then I think that there should be thousands of materials on which we can apply our approach. And so that means that the fun has just begun, and we hope to be working with many of you on either the theory or the experiment as we go along. So thank you very much for your patience, and I'll be happy to answer questions.
Thank you very much for the talk. Let's start with you.
Yeah, thank you, Zubin. Very nice talk. This effective photon mass with Hall conductivity, does it disappear if you switch off the magnetic field?
Yes. Yes.
Okay. And then does it change the sign if you turn the direction of magnetic field?
Yes. Yes, it does.
Okay, so it's just purely magnetic field effect and
Yes.
nothing more than that.
Yes.
Okay, and then why do you call this talk Pico-photonics? Why is it Pico?
So there are kind of two reasons for that. For the first case, right, this Hall viscosity can be connected to the very large momentum response of the Hall conductivity. So if you have some non-local Hall conductivity, and you start looking at very large momenta, then the Hall viscosity can be related to that. So we are really looking at ultra sub-wavelength response of matter in the presence of a magnetic field. Now, in the case of the silicon, it's much more easier to see. The field variations for that anomalous branch, it's actually sub-nanometer. So we are approaching this picoscopic regime. So that's why we think of it as the Pico-electrodynamics, because the field variations are sub-nanometer. And it's really, I mean, we are working on this, and we can show some variations over the lattice as well.
So you're going into a very short time range. Is that correct?
I would say for a fixed frequency, we are going into very small length scales.
Right.
Yeah.
Yeah. In time.
Yeah.
Next question here.
Yeah, very nice talk,
Thanks,
Zubin.
Sean.
So I just want to test something because you said that if you add a mass term to a monopole, the gap that you create is topologically trivial. If I take a monopole and then slice it in a finite KZ plane and integrate the magnetic flux, then it is unity, right? So so it would seem like a fixed M is like a slice in a monopole distribution. So why is it that the magnetic flux that you integrate is 0?
So let me try to understand this better. Yeah. So if you have like just one magnetic monopole, yeah. And so we are not saying that the monopole as such, it has a charge, so it has some flux, because the charge is 1, so it has a total flux. What we are saying is that if you try to classify a material, then you need to find the monopole in the bulk excitation spectrum. So the example that I showed you was just vacuum, right? Now what you would like to do is get that monopole in the bulk excitation spectrum of some material.
But there are wild material, right? There are wild photonic stuff and there are wild electronic stuff, right? Which are essentially monopole. Okay. That kind of monopole inside the material, right?
So it is a monopole in the photonic band structure of the periodic crystal.
Right, or right. Electronic, right?
Or electronic one.
Yeah, or electronic, yeah.
Right. Now, what we are saying is that let's take a atomic crystal and try to find the same effect. So what I was trying to show you was basically, let's look at this. So I think maybe this will be, so we're trying to bridge the gap between, let's say, a monopole that might be found in a periodic photonic crystal or a metamaterial. But now we want to find it inside, say, the material itself that is comprising the entire structure. Okay. So we're trying to bridge the gap between the atomic lattice theory and the kind of crystal lattice theory. And maybe I can mention that in a slightly different language, is that if you were to write down a field theory, this would still be a free field theory, but this would have the gauge term of the electromagnetic field physically coupled to the charges. Okay. So there would be a gauge term that is coupled to the charges in this case. And so that is something that is, I guess I did not explain the technical details. So you can actually write down that if you have a quantum optics Hamiltonian, it would essentially be kind of related to those two transverse degrees of freedom. But now inside, say, a charged fluid where the gauge field is coupled to the charges, you can actually have these Chern-Simons terms and dispersions that show that this mass that we are really talking about is related to the gauge, the U1 gauge field in QED. So does that help answer the question?
We can talk afterwards.
Okay, yeah. Okay. But hopefully this picture is slightly clearer. The one with the lattice and this one.
Great talk.
Thanks.
When you talk about the electron hydrodynamic, remind me that we actually did experiment of photon hydrodynamics in graphite, where you use a transient gradient, you generate a heat wave, and you see the photon propagating as wave. And I wonder whether in this case, do you see if you use the similar electron gradient, say light generate the gradient structure, and then you excite the electron. I guess to say one of the, what's the wave vector you're talking about?
So about the kind of first comment, actually, I think that we do see something like that. So if you have this kind of hydrodynamic model with the Navier-Stokes equation and Hall viscosity, and then you try to generate this wave packet type of thing, for this hydrodynamic model, this is a top view. This is just kind of patterned graphene. And this is where we are generating the wave packet. The edge waves go in one direction. And these edge waves close the gap. So the wave packet dynamics is interesting in this case. And in terms of the wave vector scale, so this is something that we have looked into some of the experiments in this case. And so this one actually does not, it is still qualitative, does not have the exact numbers. But I'll give you rough numbers. When we looked at the hydrodynamic model of graphene and looked at low temperatures, and we have to probe the large wave vector response in a magnetic field. So that means sub-wavelength. The frequencies that we needed were terahertz frequencies, say 1 terahertz. And the index of the prism that was needed was close to 7 or 8. So it is definitely pushing the limit, but at terahertz frequencies, we do have higher index materials. So that's the rough numbers.
Any other question?
Zubin, you were scaring me with your magnetic monopoles. So I made a different picture. Check me if I'm wrong.
Okay.
So if I take a given K vector and, for example, the spin or the electromagnetic polarization, and I move around now this K vector around some closed curve, you see some rotation or some phase shift.
Yes.
Is that equivalent to the action of the monopole?
Absolutely, with one difference. If you were to do that for the Dirac case, the phase accumulated would depend on your solid angle that you have, but there would not be a factor of 2 like in the photon case. So that's just a factor of 2 difference between kind of the original Berry phase and what others call as, say, Pancharatnam phase.
Yeah, spin 1.5, spin 1.
Exactly, that's the only difference, but you're absolutely correct. Yeah.
Okay.
Hi, thank you very much for the talk. So I want to ask, for practical reasons, how small the distances should be in materials and between materials to use this theory. For example, there is nowadays this question of how much can you confine light inside the material. And at the university, Technical University of Denmark, we make very small cavities. You can imagine something like a bow tie that has a 2 nanometer gap between silicon. There are some classical electrodynamic bounds on how much you can confine light. Now I wonder if, at this case, like 2 nanometers, if this would change if we calculate it with this theory, because also I see you're using something like the photon wave function, so it should be like a quantum theory. And there should be an uncertainty relation that maybe changes these bounds. I don't know if, for practical reasons, if we should try this kind of theories.
Right. So we have started looking into this, and I can share some of the initial insights. So for some of the Pico cavities that are there, this 1-2 nanometer regime is interesting. Now, most of that confinement really occurs from the metallic plasmons. And when we looked at that, in our case, we are still getting a Drude type response or a non-local Drude response. That means the lattice symmetries of the metal don't play a huge role. That is why we have been focused on kind of dielectric media, where the interband transitions are what determine your response functions. So that's why we looked at silicon. So in the dielectric case is where our theory has some interesting insights to offer, and 1-2 nanometer scale is sufficient. And we're still thinking about what are the real experiments to be done to look at that. Yeah.
Because we have made these cavities with 2 nanometer gaps. So if you have something to show me, like an archive or something like this.
Okay, I'll be happy to talk more.
Any other question? No more questions? Well, in that case, thanks again to the speaker.
Well, thanks everyone. On behalf of all the coordinators, I want to thank all the participants, all of you that came just for the conference, and the program participants. I think it has been a quite successful workshop, and a few collaborations being established and good discussions. So thank you everyone.
Yeah, I'd like to thank you all for coming, and some of you will be staying, and so we're looking forward to carrying on our discussions. And of course, those who will be leaving, thanks again for coming. And don't forget that you won't miss out on all the fun, because there's a Zoom link associated with the program. So if you want to carry on listening from home, you're more than welcome to do. Okay, so thanks very much again. Bye.